Okay, example 4 then. So we have our curve y equals 2 root x plus 4 over root x. We want to get the exact coordinates of any stationary points in this curve and determine their nature. So you know at any stationary point or turning point the actual gradient is 0. So there's that word gradient. Gradient means differentiate. We're going to have to differentiate at some stage, so we need to prepare the curve for differentiation. So we've got to get rid of roots and we've got to get x to the top line. So let's deal with those first. So we're going to have 2x to the power of a half, and then we're going to have plus 4 over x to the power of a half. So we're then going to slide x to the top line here in this fraction. Remember, it's only x that you ever slide to the top line, and then change the sign of its power. So that's going to give us 2x to the power of a half plus 4x to the power minus a half. So that's our curve y, ready to differentiate. So we're now going to get the general gradient. And the general gradient is dy by dx, or f dashed x. So differentiate the curve then. So a half multiplied by 2x is just going to give us x. And then subtract 1 from the power, so it's x to the power minus a half. And then multiply the term by the power, so it's going to be minus a half multiplied by positive 4, so it's going to be a negative. 4 times a half is just going to give us 2. Copy down x, and then subtract 1 from its power, so it's going to be minus 3 over 2, or minus 1.5. Okay. What we can then do again, once we've differentiated, is we can bring x back to the bottom line, and then change the sign of its power again. So if you imagine that as being 1x to the power minus a half, so the 1 stays on the top, and then slide x back to the bottom, so we're going to have x to the power positive a half, and then minus 2, it stays on the top, and then slide x back to the bottom line, we change the sign of its power. Okay. I'm happy to leave it like that for now. Don't worry about putting roots in or anything yet. Okay, so we want to get the x coordinate of the turning point. Now, to get the x coordinate of the turning point, you ask yourself what happens at the turning point. At the turning point, the actual gradient is 0. So we're going to set the general gradient, dy by dx, equal to the actual gradient at the turning point, which is 0. So set dy by dx, general gradient, equal to the actual gradient at the turning point, which is 0. So we've got 1 over x to the power of a half minus 2 over x to the power 3 over 2, and that's equal to 0. Now, really complicated looking equation, but what I'm going to do is I'm going to multiply through by the indice with a higher power. 3 over 2 is bigger than a half, so I'm going to multiply through by x to the power 3 over 2. So we're going to get x to the power 3 over 2 divided by x to the power of a half. Okay, hopefully everybody can see that. So I've just multiplied this fraction by x to the power 3 over 2. So x to the power 3 over 2 is now on the top, and then we've got x to the power of a half on the bottom. The x to the power 3 over 2's cancel when I multiply by x to the power 3 over 2, so we're just left with negative 2. And then that's equal to 0 multiplied by x to the power of 3 over 2 is just going to be 0. So it's getting a little bit better. We can then use indices rules to tidy this up. So that's x to the power 3 over 2 divided by x to the power of a half. So we subtract the powers. So 3 over 2 minus 1 over 2 is just going to give us 1. So we're now going to be left with just x to the power of 1, or just x. minus 2 equals 0. So tidy that up then. So we're just going to have x is equal to 2. So we've just worked out the x coordinate of the turning point. Now we're going to get the y coordinate of the turning point. So we're going to sub the x coordinate of the turning point into the curve. So go back to the original curve here, okay, with the roots in it, and then everywhere you see x replace with 2. So we're going to get y equals 2 times the square root of 2 plus 4 over the square root of 2. Okay. Now, you could type it into your calculator, although it may give it as a decimal. We don't want that because it says find the exact coordinates. Okay, so exact means leave roots in it, or pi in it, or e in it, or natural logs in it. So we can't have any decimals in our answer here. So what I'm going to do is I'm going to put 2 root 2 over 1. And I'm going to make the denominators the same because I'm adding fractions. So I'm going to multiply the second fraction top and bottom by root 2. Okay, so if we do that, we're going to get y equals, so if we go back down here, so we've got 2 root 2 multiplied by root 2 in the top line. So root 2 times root 2 is just 2, and then multiplied by 2 is just 4. So we're going to have 4 over root 2. And then we're adding on another 4 over root 2. So that's going to give us, again, we can write it as a single fraction now with the denominator of root 2. 4 plus 4 is going to give us 8. Now, that's not an acceptable answer because as mathematicians we've always said, see, any time you have a surd on the denominator, rationalize the denominator to get rid of the surd. So we're going to multiply the top by root 2 and we're going to multiply the bottom by root 2. So if we tidy that up, that's going to give us 8 root 2 all over root 2 times root 2 is just going to give us 2. And then the 2 cancels with the 8 outside the surd. So that's just going to leave us with 4 root 2. Now that is an acceptable answer there for the y coordinate because there's no surds in the denominator. So we've now got the x and y coordinates of the turning point. So the turning point is, the x coordinate is 2 and the y coordinate is 4 root 2. So just be careful. If it says keep your answer exact, then in this case we're leaving surds in it. Now that's the turning point. We've got to get its nature. So remember, the nature of the turning point is given by d2y by dx squared, or f double dashed x. So that means we'll have to differentiate the first derivative. So if we take it back to here, that's the first derivative, dy by dx. We're going to differentiate this. So d2y by dx squared. So differentiate x to the power minus a half, multiply by the power, we'll get minus a half, and then x, and then subtract 1 from the power, so we're going to get minus 3 over 2. Then we're going to multiply this term here by its power, so we're going to get minus 2 multiplied by minus 3 over 2. That's going to give us a positive, and that's going to give us 6 over 2. And then we're going to have x, subtract 1 from the power, so minus 1.5, subtract another one is minus 2.5, which is minus 5 over 2. Okay. Now, we're going to bring x to the bottom line to make the power of x positive, and then we're going to put roots into it because we're going to be subbing the x coordinate into this very shortly. So that's going to give us minus 1 over 2x to the power of positive 3 over 2, sliding x back down, and then 6 over 2 is just going to give us 3. So 3's on the top, and then I'm sliding x to the bottom line, so that's going to be 3 over x to the power of positive 5 over 2. Okay, plan now then is I'm going to put the roots in it. So that's minus 1 over 2 times the square root of x cubed. Again, you can put the cube bit here, the power of 3 under the root, or you can put brackets around the root and put the power of 3 outside, it doesn't matter. And then plus 3 over the square root of x to the power of 5. Again, you can keep the 5 under the root or put brackets around the root and put the 5 outside. So we've now found the second derivative. We're now going to get the nature of the turning point, so we're going to sub the x coordinate into the second derivative. So when x equals 2, the second derivative, that's going to give us minus 1 over 2 times the square root of 2 cubed, and then plus 3 over the square root of 2 to the power of 5. Now you probably could get away with just bashing the whole thing into our calculator. So let's see, if we tidy it up a little bit, that's going to be minus 1 over 2 times the square root of 2 cubed is 8, and then add on 3 over the square root of 2 to the power of 5. 2 2's are 4, 4 2's are 8, 8 2's are 16, times another 2's 32. So I think that's sufficient to bash into calculator, and let's see whether it turns out to be positive, negative, or 0. Okay, so that actually turns out to be root 2 over 4. So it's positive, yeah, positive root 2 over 4, or 0.353. So that's clearly greater than 0, so therefore the turning point is a minimum. Okay, so final answer. The point 2 for root 2 is a minimum. Okay. So another very good example there. You need to be good with indices in particular.